Good morning, ladies and gentlemen. All right, here is Calc Review 15. So I chose, a handful of the problems that were most asked about. If I don't cover your question here, then email me and I will make a separate video on it, or check your peers' response because a lot of the questions were answered by your peers in a very nice way. Even some of the questions that I do here were answered in a very nice way, but I just figured I'd make a video on these questions because they were asked about most often. So we're starting out with this problem, part B. Explain why there must be a value C between 1 and 3 such that h prime of C is equal to -5. And all we're given is the information in this table, as well as the fact that our function h is equal to f of g of x minus 6. There are two ways you can approach a problem like this. You can either use the intermediate value theorem, where you actually find values of h prime and hope to find one that's less than -5 and one that's greater than -5. And if that's the case, and since h prime is continuous, you'd be able to make the claim that there's a value such that h prime is equal to -5. If you tried that out, you would find that we don't have the ability to do that here. So we have to rely on the mean value theorem. Now, the mean value theorem tells us to find the average rate of change of h on n interval between 1 and 3. So I just chose the endpoints x equals 1 and x equals 3, and I found the average rate of change of h on this interval. You can use the table to determine that h of 1 is equal to 3, h of 3 is equal to -7, and so when we do average rate of change, we find the slope of that secant line basically. So we do the change in y over the change in x, and we get -5. So since f and g are differentiable, which we are told here, since they're differentiable, they are also therefore continuous. And since h is just a composition of these two functions and also a constant, this means that h is also differentiable and continuous, okay? So this is a necessary statement. All of the work that I'm highlighting is basically necessary work. So showing this average rate of change, specifying that you know that h is differentiable and continuous. Now that we have all that information, we can now use the mean value theorem. We can now make this last statement. By the mean value theorem, there must exist a c in between 1 and 3 such that h prime of c is equal to -5. All right, and there you have it. So that's how you would approach a problem like part B using the mean value theorem. Part D was asked about a lot, where we have some inverse function of g, and we need to write an equation for the tangent line to the graph y equals g inverse of x. And we're told we want to do it at x equals 2. All right, first of all, the equation of a tangent line in general can be found by finding the slope at a point times x minus the x coordinate, and that will equal y minus the y coordinate. All right. Rather than using the inverse notation, I'm just defining a new function j of x, which is going to be inverse of g. And so by definition of inverse, if I compose the two functions g and j, I should get x actually. Sorry, I wrote it as 1, but this should say x. Right, and that's the definition of an inverse. Now, I'm going to differentiate both sides. And the left side is a composition, so I need to use the chain rule. The right side, when I differentiate x with respect to x, the right side just ends up being 1. So the left side gives you g prime of j of x times j prime of x. The right side is equal to 1. I'm actually interested, though, in j prime of x, because ultimately I want to find the slope of a tangent line, or the equation of a tangent line at some point along the inverse function j. So solving for j prime of x, you see that j prime of x is just equal to 1 over g prime of j of x, and that's going to be our slope. All right, now we actually have to find the specific value at the specific point, and so we'll do that in just a moment, but this is going to be the expression that we use to get our slope for our tangent line. All right, so updating our values, instead of m, I have j prime of 2, right? Instead of x here, I'm writing 2. Similarly here, I'm going to multiply my slope by x minus 2, and that's going to equal y minus j of 2. So there's still some information I need to determine. I need to determine j of 2, and I need to determine j prime of 2. So let's start with j of 2. Let me use a different highlighter color. So I'm going to set up the equation that says j of 2 is equal to some value, and I use question mark. I don't like this highlighter color, so I'm going to change it. Let's use green. All right, so I set up this equation. By the definition of inverse, if I apply g to both sides of this equation, on the left side, I just end up with 2. On the right side, I have g of question mark. And we can go up to the table and see what value do we have to plug into g to get 2. What value do we have to plug into g to get 2? Well, here we see g being equal to 2, and it looks like we have to plug in 1. So g of 1 is equal to 2. That's what that information tells you. And so that means the question mark must equal 1. All right, so what we've established here is that j of 2 is equal to 1. Okay, j of 2 is equal to 1. And now let's go on and determine what is j prime of 2 equal to. Well, using this formula here, j prime of 2 is equal to 1 over g prime of j of 2. And we just determined that j of 2 is equal to 1. And so this breaks down to 1 over g prime of 1. And you can go up to the table and check for yourself that 1 over g prime of 1 will just give me 1 over 5. And so my final answer would be the one in blue here, where the slope is 1/5 times x minus 2 is equal to y minus 1. That is the overall equation of your tangent line to the inverse function at x equals 2. Okay, hopefully that made sense. Moving on. The next question that was asked about was part C of this problem. And I don't think it was asked about too often, but I definitely wanted to bring it up because it's a U-sub problem, and I think some of you are kind of afraid of U-sub, but it's so simple. I just want to keep showing it to you so you hopefully understand how simple it actually is. So we have to somehow evaluate this integral, this definite integral, but we happen to have a composition. And so whenever you're trying to integrate a composition, one of the first things you should do is try U substitution. If U sub doesn't work, then we actually won't know how to do it. We haven't learned those methods in AB calculus. Now, so of course with U sub, the first choice of U should be the inner function, which is 2x in this case. So I set U to be 2x, du then would be equal to 2 dx. just so you can follow along. So u equals 2x, which if I differentiate both sides, I have du is equal to 2dx, and I want to replace dx. So I'm going to just sort of solve this equation for dx, and I see that du over 2 is equal to the differential dx. All right, so down below here, I've made some replacements. Instead of dx, I've replaced that with du over 2. I just happen to pull the 1/2 out front, and that's fine. Instead of 2x here, I have u. And the one thing that is often overlooked is the limits of integration also need to change, because when we're integrating from 1 to 3, that's with respect to x. We are now integrating with respect to u, so we need to adjust and update our limits of integration. So instead of 1, I'm going to take this 1 and I'm going to plug it into our equivalency for u. So when I plug 1 in for x, I get 2. So my lower limit of integration is now going to be 2. When I plug 1 in for x, when I plug 3 in for x, I get 6. So my new upper limit of integration is going to be 6. All right. I just erased things by accident. This is 1, this is 6. Plug this in here. And that, okay. So my limits of integration have been updated, and now I can just sort of do a direct definite integral. So the antiderivative fundamental theorem of calculus part 1 tells me that to evaluate a definite integral, I have to find the antiderivative and evaluate that at both the upper and lower limits, and then subtract those two terms. Well, the antiderivative of f double prime is f prime. Okay, that's what we see here, f prime of u, and I'm going to evaluate that at these two boundaries. Please don't forget the constant. Okay, so in our next line, we have that constant times f prime of 6 minus f prime of 2, and these values can be determined by looking up here at the table. Very simple, and so we end up with our final answer, which is 1/2 times 5 minus -2, or of course just 7 over 2. All right, and there you have that. I'm just double checking my table value lookup skills. Yeah, that looks good. Okay. All right, so your final answer will be 7 over 2 there. All right, and let's see. All right, second to last. This one's kind of long. Part D. For this interval, for some t between 0 and 60, must there be a time where a of t is equal to 0? So this one's a little tricky. You're given a table of values with a whole bunch of values of a. And so you might say, maybe the intermediate value theorem would work here. Like if we were given a value of a that was negative and one value that was positive, then it would be simple to use the intermediate value theorem, because acceleration is constant, continuous, I should say. Acceleration is continuous, and if we knew that one acceleration was negative and one acceleration was positive, then that would guarantee by the intermediate value theorem that there must be an acceleration that was equal to 0. But nothing in our table actually indicates that at these particular points, right? So we need to somehow gather that information in another way. Well, first, of course, with a problem like this, let's always state right off the bat that we know our functions are continuous. And in this case, we're told that that is the case. Right here. I want you to notice that the velocity changes from -20 to -30 from t equals 0 to t equals 15. In other words, in that time frame, velocity has decreased. And of course, if velocity is decreasing, that means acceleration is negative, right? That means the slope of velocity, which is acceleration, is negative, at least at some point along that interval. So I make that claim here. Since v of t changes from -20 to -30 over this interval, we can therefore say that a of t must be negative at some point from t equals 0 to t equals 15. And that's just due to the mean value theorem. All right, the second argument we're going to make is that v prime of t changes from -30 to -20 from t equals 15 to t equals 25. And so similarly, this must imply that a of t is positive at some point on this interval. Okay, putting all of this together, since we know that a of t is continuous, and since we also know that there was a negative acceleration, which then became a positive acceleration over this time frame, that means at some point acceleration must have been equal to 0, right? We're told acceleration is continuous. We know that at some point acceleration was negative. We know that at some point acceleration was positive. Therefore, at some point within that interval, acceleration must have also been equal to 0. And that is by the intermediate value theorem. All right, so that's a kind of a beast of a problem. It really shows an understanding of sort of what's going on with the relationship between velocity, acceleration, or more generally, functions and their derivatives. But there you have it. That would be a solution to that problem. And lastly, part A was asked about, and I just also think it's a really good problem. For these values between 0 and 4, find all values of x at which f has a relative extremum. In other words, a relative max or relative min. And also make sure to determine whether they are either a max or a min. And of course, justify your answers. So first of all, the candidates for relative extremum are they basically the critical points. So that is, when is f prime equal to 0 and when is f prime undefined? So going through the table, you'll notice that f prime is equal to 0 when x equals 1, and f prime is undefined when x equals 2, and there are no other points that fit that criteria. And so these are the only candidates for relative extremum. Right, x equals 1 and x equals 2. So what I'm going to do next to determine if they are actually extrema, and more specifically if they're either a max or a min, I'm going to put them on a number line. And I'm going to use the first derivative test. So I'm going to evaluate f prime at these points. Well, let's look at when f prime is 0. What happens to the derivative around that point? Well, f prime is positive on the left, f prime is positive on the right. And so this information sort of tells us that when x equals 1, f has neither a max nor a min. All right, so maybe at x equals 1, the graph kind of, well, if f prime is positive, that means the function is increasing. It flattens out for an instant and then continues to increase. So this might be what the graph looks like when x equals 1. Okay, well, let's look at the other one when x equals 2. We know that the derivative is undefined. Now this could mean a couple of things. This means that either the function itself is undefined at this point, in which case it's impossible for there to be a min or a max, or it might mean that there's like a corner or a cusp. So we do need to pay attention to the original function here too. Is the original function defined at x equals 2? And if we go up here, we do see that f of x equals 2. That's important information. So when x equals 2, we know that y is equal to 2. We also know that the derivative is undefined at this point. So this is kind of indicating to me that there's likely, on the graph, there's likely a corner. We know that to the left of x equals 2, there's a positive derivative, which means that f is increasing. And then to the right of x equals 2, we are told that the derivative is negative, which means that f is decreasing. And it must do so at like some kind of a corner or a cusp. I don't know exactly, but I mean, I drew this to kind of look like a corner or a cusp. And this is probably, this is something like what the graph might look like at around x equals 2. But as you can see, since the derivative goes from positive to negative, this happens to be a max. All right, and that will be our argument that we make. We say that there is a relative max on f at x equals 2. Why? Because f prime changes from positive to negative at this point. And there you have it. All right, ladies and gentlemen, I tried to go through that as quickly as possible. Of course, you could always pause it, slow it down if you, and kind of make me repeat something if necessary. So that's the beauty of videos. I hope this helped. Again, if I didn't cover your question, please email me and I will make sure to make a video that does cover it. But until then, ladies and gentlemen, have a great day. Talk to you tomorrow. Bye.